Problem 3 says carbon monoxide can be combined with hydrogen to produce methanol, CH3OH. Methanol is used as an industrial solvent, as a reactant in some synthesis reactions, and as a clean-burning fuel for some racing cars. If you have 152.5 kilograms of carbon monoxide and 24.5 kilograms of hydrogen gas, how many kilograms of methanol could be produced and how much excess will remain? So let's first start by writing out our reaction. So carbon monoxide, so just CO, is combined with hydrogen, and I know hydrogen is a diatomic, so it'll be H2, not just H, to produce methanol, and it gives us the formula CH3OH. Now we need to balance our reaction here, and I notice that I have one carbon and one oxygen on each side, but that my hydrogen is out of balance. I have 4 hydrogens on my product side and only 2 on my reactant side, so I'm going to double my H2. So 1 carbon monoxide and 2 hydrogens give me 1 methanol, and there's my balanced reaction. Now I need to figure out which of my reactants is going to be limiting, and I'll do that by converting my 2 given values, so the 152 kilograms of carbon monoxide and the 24.5 kilograms of hydrogen, to an amount of product. I'm just going to convert to moles of product, or moles of methanol. Now, my reactant amounts are not actually given in grams, they're given in kilograms, and I know that my molar mass values are given in grams, so what I'm going to need to do is to convert the values to grams before I can actually use my mole conversion chart with my molar mass. So I'll start by doing that. So 152.5 kilograms of carbon monoxide. So I'll start out by converting kilograms to grams, and since there's always the same number of grams in a kilogram, I don't need to put my substance here. 1 kilogram always equals 1,000 grams. And then now that I'm in grams of carbon monoxide, I can do grams of carbon monoxide on bottom to moles of carbon monoxide on top. And then I will go from moles of carbon monoxide to moles of methanol, CH3OH. Then I'll do the same thing for my hydrogen gas. So I'll start out with 24.5 kilograms of H2. And I'll start out by doing my kilograms on bottom and grams on top, so 1,000 grams in 1 kilogram. Then we will take our grams of H2 to moles of H2. And then we'll do our mole-to-mole step where we go from moles of H2 to moles of our methanol, CH3OH. Oh, and not at times, I'll do an equal sign there. And so now I'm just going to calculate this out. So 152.5 divided by, or times 1,000, times 1,000. And I didn't actually put in numbers yet, so I'll need to do that before we can actually calculate. So I'll start out with my mole-to-mole ratio. We can look back at our reaction to determine that. So CH3OH has no coefficient, so that's going to be a 1. 1 mole of CH3OH. And then moles of CO also doesn't have a coefficient, so I know a 1's implied there as well. And then H2 has a coefficient of 2, and so we'll put a 2 down here next to H2. Then we need the number of grams per mole. We know that 1 mole of hydrogen is going to equal to 1 times 1.008 grams, so it's about 2 grams of H2 in 1 mole. And then carbon monoxide, 1 mole of carbon monoxide is 12.011, sorry, I was having a hard time speaking, plus oxygen, which is about 16. So 12 plus 16 gives us a mass of about 28 grams per mole. Okay, so now that we have numbers, we can continue. So 152.5 times 1,000 divided by 28 times 1 divided by 1. So that's just going to be the same thing. I don't need to type that in. So I got 5446.4. And that would be my moles of CH3OH. Notice I'm not really rounding to sig figs here because this is an intermediate value, but we're close. We could go ahead and round to 4 sig figs if you desire, but we're not all the way at our theoretical yield because it's asking us how many kilograms of methanol could be produced. We actually have a couple more steps to go there, so I'm just going to leave it as is for now. And then we'll do our second problem. 24.5 times 1,000 divided by 2 divided by 2 again. And this time I got 6125 moles of CH3OH. So this is really large numbers here, really big numbers of moles. But our smaller number comes from our carbon monoxide. Our hydrogen gas actually produces more moles of methanol. And so so there we have it. So our limiting reactant is going to be the carbon monoxide. So I'll go ahead and label that in the problem. This is our limiting reactant. And the reactant available in excess is going to be our hydrogen. So we'll have excess hydrogen. And so I'm going to go ahead and cross this one off, and we will continue converting our theoretical yield. I'll label that as well. This is our theoretical yield. We'll convert that into the desired unit, kilograms of methanol. So first we'll have to go from moles of CH3OH to grams of CH3OH. And then once we do that, we can go from grams to kilograms. I know 1 kilogram equals 1,000 grams. And I'll have to add up the molar mass here. 1 mole CH3OH, so 12 plus 3 times 1 plus 16 plus 1. And so when I did all that, I get about 32 grams per mole. So there we go. We got our molar mass. Now we'll just multiply this out. So take that number that we got before, that 5446.4 times 32 divided by 1,000. And what I get when I do that is 174.2857. And of course we will have to round to sig figs at this point. So looking back at our given value, we have 4 significant figures there, and so our answer will also be rounded to 4 significant figures. So I'll keep those digits, and then look at the 8 to figure out where to round. So I'm going to round this to approximately 174.3 kilograms of CH3OH, methanol. So there is our theoretical yield in the desired unit. I'll box that part in. Now we just need to figure out how much of our reactant available in excess was actually used, and then from there we can figure out how much remains. So I always like to start with my theoretical yield in moles and then work my way back to how much of the reactant was used. So I'm going to do that now. I'm going to start with my 5446.4 moles of CH3OH, and I will convert my moles of CH3OH to moles of hydrogen, and then we will convert moles of hydrogen to grams of hydrogen, and then I'm going to just go ahead and convert it to kilograms, grams to kilograms. So then we'll fill in those numbers. I know 1 kilogram is 1,000 grams. 1 mole of H2 is approximately 2 grams of H2. And then from our chemical reaction, for every 2 moles of H2 that are consumed, we are able to make 1 mole of CH3OH. So we will plug all that into our calculator. And when I did that, I got 21.79 kilograms of H2 that were used up. So then we just need to figure out how much is left. So we will start with the amount that we had. So the 24.5 grams, we'll start with that. 24.5, or not grams, kilograms, sorry, of H2, and subtract out the amount we used, the 21.79 kilograms of H2 were used up. And so when we subtract that out, I got 2.71, but of course for sig figs in addition and subtraction, we look at decimal places. So I have 1 decimal place here and 2 decimal places here, so our answer is actually going to round to just 1 decimal place. So I'm going to round to approximately 2.7 kilograms of excess H2. And there is our remaining amount of H2 at the end of this reaction. And so let's just double check that we've done everything. It says how many kilograms of methanol could it be produced? Well, right there's our theoretical yield, and then how much excess reactant would remain, and there it is. So we have indeed done everything that the problem is asking for.